All right, another topic that we're interested in with regard to a graph is symmetry. Does the graph we're looking at have symmetry? And symmetry is defined as when you reflect the graph across a given line or axis, a given line or an axis, the x or y axis, the graph is a mirror image. We say that the graph is symmetrical with respect to that axis. Okay, so let's go ahead and depart from the notes for just a second. I have another handout, okay, where we have a collection of graphs here, and I wanted to just present you with just examples of even, odd functions and neither functions, which is all ties in with symmetry. Okay, so let's take a look at what it means to be an even function. Okay, all three of these graphs across here, across this row, are called even functions. Okay, even functions have y-axis symmetry. So if we have y-axis symmetry, then the function is said to be an even function. So just think about where the y-axis is. If you were to take and fold along the y-axis, then that fold is going to create a mirror image of the graph. Okay, and same thing here, and same thing here. And digging in a little bit at some specific points, let's just come up with some ordered pairs, because numerically we want to look at symmetry as well. Not just graphically, but looking at the numbers. So if I just chose the point -2, 4, and let's just say this is the ordered pair -2, 4 on this even function that has y-axis symmetry, well, then that means that +2, +4 has to also be a point on this even function. Notice that the x-coordinates are opposite, but we're at the same height, the height of 4. So x's are opposites, but the y's are the same. So I'm going to come over here and just kind of introduce you to some notation that we're going to see in more detail in a minute. Okay, so let me just write that out first, and then I'll put the notation. So we have opposite x's for even functions, but the same y's. Okay, and another way to say that using notation, which I know that's the tricky part of math, is this. F of x equals f of opposite x. So when we look at this, we can see that the two x values are opposites, okay, but the two actual y values represented by the notation f of x and f of negative x, that's a notation for a y value, those are actually equal to each other. And sometimes you might see f of negative x on the left-hand side of the equal sign and f of x on the right-hand side, okay? So just kind of going along with that idea for just a second, let's look at a couple of points on this even function that has y-axis symmetry. So if we chose the point -3, +3, what would be a point that's on this even function, knowing that this is an ordered pair on this function? Well, opposite x's, so that means it's +3, but we keep the second coordinate or the y the same. So opposite x's, the same y's. And we can do the same thing over here. We could choose a point. So if I chose the point 1, -4, and I knew this was an even function, then I would have to know that this point that's symmetric with it, that its mirror image here, okay, is going to be -1, the opposite of that, but the same y. All right, what does it mean for a function to be odd? Well, there's symmetry going on with regard to odd functions, and actually it's a double kind of symmetry situation. Okay, this is said to have origin symmetry. Odd functions are symmetric with regard to the origin. Here's the origin in these graphs right here. It's actually a double reflection that creates the mirror image. Meaning we have to reflect across either the x or y axis first, and then once we do that, we have to do one more reflection across the remaining axis. So for example, if I looked at this graph right here, if I were to take this graph that's in quadrant 1, this is quadrant 1, 2, 3, and 4. If I were to take this graph and just kind of focus on this part of the graph right here, a little piece at a time, if I were to reflect across the y-axis, that reflection would create this mirror image. But the origin symmetry means I've got to go kind of through the origin. I have one more reflection to go across the x-axis. So now with this part of the graph right here, if I reflect it again, what's going to happen is it's going to lay on top of that part of the graph that's already there. So I'm going to go ahead and erase this. So a double reflection, origin symmetry, odd function. Let's kind of dig in and look at some specific points, and then we'll also look at the notation that represents this. All right, let's consider that we have this point right here, this ordered pair 1, 1. This is the point over 1, up 1. If we had an even function, then over here, its reflected point would be negative 1, 1. But what's happening is we're actually down here at its corresponding image point is negative 1, left 1, and down 1. Well, notice what happened to these two coordinates to get these two new coordinates. We had to take the opposite of both x and y to get this mirror image here. So let's do another point. Let's do 2, 4. What if 2, 4 is a point on an odd function? So what other ordered pair would be on the same odd function? Well, it's opposite x's and opposite y's to get you down here in this quadrant. So think about negative 2, negative 4. Well, from the origin, if we go left 2 and down 4, yep, I'm going to land on this other part of the graph. So this is an odd function. It has origin symmetry because of that double reflection. All right, look at the middle graph here. So is this an odd function? Well, no, let's kind of visualize it. Just choose a section of this graph. I'm going to happen to choose quadrant 2. What if I were to reflect across the x-axis first? Well, that would put the graph like down here. But then I still have another reflection, which means I have to go across the y-axis. And if I was better at drawing, then the graph would actually end up, this part of the graph, through a double reflection, would create this mirror image here. So yes, this is another odd function. It has origin symmetry. And another way to think about it is, if a function is going to have origin symmetry, then it has to at least go through the origin. So let's look at some points here. Let's consider this point right here, negative 1, 3. If negative 1, positive 3 is a point on an odd function, then take the opposite of these two coordinates, positive 1, negative 3, and that should be a point that's also on that same function. And it is. All right, and here's another example of an odd function. We could do the same thing we did here by choosing an ordered pair, taking the opposite of both the x and y coordinates, and verifying that that's also a point on the same graph. Okay, so I'm going to come up here and add a few more things before I go to this last set of functions that I've drawn. So remember, a double reflection means that you've got to go across both the x and the y axis. The x. And it doesn't matter what order. You can go across the y first and then the x later. Okay, the notation's a little funky, so let's look at that. So how do these two ordered pairs, how do they relate to each other, these numbers? Well, the x's are opposites. So if I had positive x here, then I would have to have negative x in here. This is input value right here. These are your x's. So opposite x's, but then we pull back and we look at all the notation. What would represent opposite y's? Well, I've got to make one of these, and typically we make it this one, have a negative in front of it. Either I need to put the negative in front here or the negative in front here to indicate this is a negative y. So I've showed opposite x's, and then I've showed opposite y's. The notation is a little strange, I know that. All right, so let's look at these last three functions down here. I've said that these are neither functions. Okay, so there's no symmetry with regard to the y-axis, so this is not an even function. This graph doesn't even pass through the origin, so it can't even possibly be an odd function. Okay, this function is not odd, and neither is this one, because neither one of these go through the origin. Even functions. In order for this to be an even function, when I reflect across the y-axis, this graph right here should land on top of itself, create a mirror image of itself. And that would only take place if you had a graph that looked like this. But that's not where this part of the graph is in quadrant 2. So if you fold it along the y-axis, the graphs would not coincide and lay on top of each other. And same thing here. If you fold it across the y-axis, okay, you're not going to coincide with what's already there and present as part of the graph. So hopefully this kind of gave you an idea of symmetry, and then also classifying functions as even, odd, or neither. Okay. Now I'm going to return to the notes. And actually, I'm going to go to the third page of the notes. And I'll come back to the second page. But I want to just kind of do some more inspection of even odd functions. So, come down here. Right above here, there's just a collection of graphs. Some of the grids didn't come through, but we'll just kind of look at the graphs that are there. Okay, for this example right here, okay, and for all of them, I tell you what, classify these functions as even, odd, or neither. So you might want to pause the video and put even, odd, or neither above each of these 5 different graphs, and then come back and check how you did. All right, graph A, that's odd. It has origin symmetry. A double reflection creates the mirror image. Definitely not odd and definitely not even. So I would say that this graph right here is neither. Graph C, not odd, doesn't go through the origin, so it looks like it has y-axis symmetry, so we're going to say it's even. Remember, it's y-axis symmetry. Okay, top right. Definitely not even. I don't have a reflection, just the x-axis. But is it odd? That one's a little more tricky. So let's kind of look at individual points. It does pass through the origin, so it does require some attention here. I'm going to choose this ordered pair up here at -1, 2. If this is an odd function, I would have to take the opposite of both these coordinates, make this 1, -2, and 1, -2 would have to be on this graph. If it's not, then it's not going to be odd or origin symmetry. Well, it just so happens this is the ordered pair 1, -2. I might just investigate another ordered pair just to make certain, because I'm just basing my decision on, with points anyway, on just 2 ordered pairs. I might want to think about this point right here as being maybe -1/2, +1. So is the point +1/2, -1, +1/2 is over here, -1 also a point on this graph? It sure is. So then I began to think, okay, well, let me just choose a section of this graph and do a double reflection. So I'm going to choose maybe what's down here in quadrant 4. If I reflected across the y-axis, then that graph would be somewhere like right here. Then if I took and reflected across the x-axis, then I would have a mirror image up here. Then the graph would lay on top of itself with the double reflection. So yes, this is an odd function. We have origin symmetry. And the last graph, it's kind of hard to see, but this was the y-axis right here, and I think this was the x-axis. Wait, this must have been the x-axis. I guess that didn't come through in the copy process. Let me see, make sure. No. The x-axis is up higher. So this is actually the x-axis. So definitely not an odd function, doesn't pass through the origin. But does it have y-axis symmetry? Sure. If you were to fold along the y-axis, you create a mirror image of the graph over here. So hopefully, given a graph, you're going to be able to identify whether the function's even, odd, or neither, just based on what we've done here. Okay, in a minute, we're going to come back to these 2 problems right here where we have to determine algebraically if these are even or odd functions. Without looking at a graph, how do we take an equation to determine if a function's even, odd, or neither? We're going to come back to that in a minute. Now we're going to go back to the other page of our notes and continue from there. All right, back to symmetry, even, odd functions. So you'll see a lot of our work was already done in this. So an even function is called even if it demonstrates symmetry with respect to the y-axis. An example of this is the quadratic function y = x squared, which is also called a parabola. Algebraically, if we have an even function, the x's are opposite, but the y's are the same, meaning there's not a negative in front of one of these notations. Graphically, it means that for any point xy on an even function, there exists a point having opposite x coordinate, but the same y coordinate. So we kind of already talked through that. Okay, what I want to do over here is to get us ready for the next section too, is I want to show you how y equals x squared becomes what it looks like. So oftentimes when we want to create a graph and we have an equation, we create what we call a t-chart. And so down the left column here, I'm going to label the left column my input values, my x's, my domains. And then over here, a label on the output column or the right column is going to be y, sometimes called f of x. You could even put y equals x squared. Okay, any of those will work. Well, how do I produce a graph of y equals x squared? Well, it's kind of common practice to build this t-chart, and we usually choose some negative integers and some positive integers as x values. So I have a choice of x values. I'm going to choose from -1 to, from -2 to +2. I'm going to choose those integers. Now I could choose a bunch of points in between, but that's just going to make my work harder. But I could have chosen some decimals in between here. Okay, so what do I do with each of these x values? Well, I one at a time insert them in for x and do the work, and then I report the corresponding y that goes with each of these x's to where I get an ordered pair that I could plot and then connect and draw a graph. So plug in -2 and square it. You're going to get 4. Any negative number that you square becomes positive. So that's 1. 0 squared is 0. This is 1 and this is 4. Before we go over here to the graph, remember this is an even function. So look at these two x's. These are opposite x's, but they give you the same y's of 4. Look at this other set of opposite x's, -1 and 1. They give you the same output, the same y. So on an even function, we've already seen that, but this is just kind of a table to organize that. Now let's take each of these and plot them as ordered pairs on our grid. So -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. And we can see the symmetry of these points through the y-axis. All right, now we want to connect these points, these ordered pairs. And just because these are the only x's I chose in my table doesn't mean that this graph ends. As a matter of fact, I can input any x value I want and square it, so the arrow suggests that that can take place. And then here, I'm going to swing around. It's not sharp, it's real rounded here. And then I'm going to extend off the grid a little bit. So it says an example of an even function is this quadratic function y equals x squared, which also has the name parabola. So algebraically, we have opposite x's and the same y's. Graphically, we have x coordinates that are opposite with the same y's. We've seen all that. All right, let's go down here to odd function. So a function is called odd if it demonstrates symmetry with respect to the origin. An example of this is the cubic function. So this was quadratic, high exponent of 2. This is cubic, high exponent of 3. This symmetry is definitely harder to see than the even function, but it is thought of as that double reflection, first across the y and then across the x. But again, you can go x and then y. Algebraically, what does it mean to have an odd function? Well, it means the x's are opposite, like we have here, and then the y's are opposite as well. There's a negative on one of the notations that represents the y's. And then graphically, for an odd function, if you have an ordered pair that's xy, then we take the opposite of each of those coordinates, whatever they might be, to get another point that's on that odd function. All right, let's see what y equals x cubed looks like. This is going to help us with our work in the next section. All right, I'm going to choose, it's kind of common practice, if it works, to choose these same 5 integers here. And then I'll put y here, but remember our new y is x cubed. We can also call this f of x because that's the notation that represents a y. So let's put -2 in and multiply it by itself 3 times. So that's -8, -1, 0 cubed is 0, 1, and 8. Before we go over here and graph these ordered pairs, let's remind ourselves, let's look at this set of x values, -2 and +2. So now let's look at the y's that go with them. They're also opposites. So if -2, -8 is a point on an odd function, then I have to make both these positive, which they are down here, to be on an odd function. Like -1, -1, take the opposite of both those, and you're going to end up with positive 1, which is also present in this table. All right, let's see when we plot these points and connect them that we can see can visualize the origin symmetry. -2. Okay, -8's off my grid, but I'll just estimate it's down here. -1, -1. Looks like I got 0, 0, and then 1, 1. And then 2, 8's probably going to be off the grid too, but I'll put it up here. So when I draw this, I know that I could continue down this way. I'd put an arrow down here, and I'd come up here. I want to be careful how I draw that. Kind of move up this way. Don't want to go backwards. I want to kind of come up here and grab this point, kind of bends into the origin, then bends back this way to pick up that point, and then continues upward this way. And go ahead and extend off those points and put arrows on them. Is the visual of this cubic graph suggesting that we have an odd function? Yes, it does. All right, something else in the equation, because that's where we're moving to and transitioning to next, is looking at equations and determining if those produce even or odd functions. But just kind of an observation right here. If your equation is y equals x squared and there's not any other terms, look at the highest exponent on this polynomial function. It's even. If that's an even power and there's not any other terms here, you can bet it's an even function. Likewise, if you're dealing with this polynomial and there's only one term and that term has a odd exponent like this, then you know you have an odd function. Now, if you have other terms in the equation, other things here, then we have to do something else. And that's what we're about to do right now, okay? So continuing to look at even and odd functions, now let's go back to this page. And we're going to look at example 1 and 2. All right, determine algebraically if a function is even or odd. We don't have a graph to look at. And I certainly don't want to create a table of values. That's tedious. Okay, so what do? We have to evaluate the sign changes in f of negative x and compare to f of x. You're probably going, what does that mean? I don't blame you. Okay, so this is the process. We have to determine if a function is even or odd. So we know that if it's even or odd, at least we know the x's have to be opposites. We know that to be true. So we're going to take that equation, and everywhere you see an x in it, I'm going to put a parenthesis. And every x I see, starting with this x right here, is going to be changed to the opposite of x. Negative x here and negative x here. And be careful about your parentheses and where you put your placement of your power. So it says evaluate the sign changes in f of negative x and compare to f of x. So, all right, so replace x's with negative x. Now I'm going to keep this notation f of negative x. Bring it down. You have the equals. We've got to clean this up a little bit. Okay, so next we have to clean this up, meaning what is negative x taken to the third power? Well, that's the times. Okay, let's handle the multiplication first. What's a negative times negative times negative? Well, with an odd number of factors, and they're all negative, your answer is going to be negative. So I know my answer is negative. If it was even, then I would be at a positive answer. So then we look at the variables. We dealt with the negatives first. Now let's look at the variables. What's x to the first times x to the first times x to the first? Well, that's x cubed. So when I clean up this right here, this term, I'm going to get negative x cubed. Now let's move on. Now I'm subtracting a negative x. Well, subtracting a negative x is going to return that to plus x. So again, what we did is we replaced every x with negative x. We did some cleanup. Now what it means is to evaluate the sign changes and compare to the original function. Okay, let's look at this answer compared to this function right here. Is every term in this answer the opposite, terms are what you add or subtract, is everything that you landed on down here the opposite of what it was originally? If this is negative x cubed and that was positive x cubed, those are opposite terms. this is positive x and that's negative x, then that term is also the opposite. So that means that this y right here, this represents a y, is completely opposite, or the opposite, the negative of what I started with. So I just learned that this function, this original function, is odd. So this is called an odd function, or it has origin symmetry. I'll call that origin symmetry. So put a little note to yourself. And if you look at my key, I usually have my key more developed than what I do here because I have more time for that key. But once we perform this set of steps, we look and say, oh, if all terms of f of negative x, meaning these terms right here, are opposite of terms of f of x, these original terms, then f of x, the original function, is odd. And it can't just be one or two terms. It has to be every single term has to be the opposite. If not every term, if not all are opposite, then it's not odd. Okay, let's look and see what happens. Oh, before I go on to this one, another reason you can think about this being odd is look at the I do have multiple terms, but look at the exponents. 3 is odd and 1 is odd. As long as I don't have a constant here, like a +5 or a -2, okay, if all I have are variables and all the exponents are odd, then that's kind of a quick way to say, well, I think that's going to be odd and make that prediction. But I would certainly go through the verification process. And mathematically, algebraically, this is how you verify if a function is even, odd, or neither. Okay, let's look at 2. So by inspection, look at the exponents. Okay, that's not considered, that 2 is not considered a constant. It's called a coefficient because you're multiplying. Constants are just numbers that you add or subtract that don't have variables. But just inspect the 2 exponents. They're even. My prediction is that this function is going to be even. How do I prove that? Well, everywhere you see an x, replace it with negative x. So negative x goes there and negative x goes there. But first we have to do a cleanup. So bring down f of negative x again. All right, what's negative x times itself? Well, take care of the negatives first. 2 negatives, an even number of negatives means your answer is going to be positive. And then x to the first times x to the first is x squared. So I'm doing order of operations, the power first. This returns x squared, but I still have to multiply it by my coefficient, 2x squared. Now let's come over here. What's negative x to the 4th power? Well, just think about what that means. There's 4 negatives to be multiplied. My answer is going to be positive. And then when I multiply the variables, I get x to the 4th. So this is plus right here. So I keep it as plus because all I've done is focus my attention on cleaning up this expression. So plus x to the 4th. Now compare this answer with the original answer. All signs the same, even. All signs opposite, odd. This is an even function. Y-axis symmetry. I'm just going to put down here abbreviated, all terms the same. I mean, these terms compared to that terms means that we have an even function. All terms opposite compared to the original, odd function. And we're just about to wrap this up, but I'm going to do one more example. And so I think I'll do it on the back of this if you have the back available or somewhere else. Okay, let's say we have this function right here. And we don't have a graph to look at to inspect to see if it's even or odd. We can't see what the symmetry is. So what do we do to determine if this function is even, odd, or neither? First step, write the problem down, but everywhere you see an x, put a parenthesis. Now insert opposite x's, because if it's even or odd, remember our x's are always going to be opposite. And then we just look at the y, the answer we get. All right, let's take care of cleaning this term up first right here. This is a term, so negative x cubed would be negative x cubed times 3. All of that results in, I'll pull the negative up front, negative 3x cubed. So this is negative x cubed times a 3. I don't have to do a power here. I just have to distribute this negative inside that parentheses. So that turns that to positive x. There's no sign change here, so I just bring down plus 2. Now compare these 3 terms with the original 3 terms. All signs the same, all signs different. Well, these 2 terms have opposite signs. These 2 terms have opposite signs, but that 2 is the same as that 2. So all signs are not opposite, nor are all signs the same. So there is no symmetry on this graph. It's a neither function. So I hope that helps. I will try and come up with a short video that just has 4 or 5 examples of determining whether functions are even, odd, or neither by using equations. It is a commonly missed thing on tests and stuff, so it just suggests that we just need a little bit more practice. So I'll set up a short little video that does some real quick practice problems of determining algebraically from an equation if a function is even, odd, or neither.